In this video, I'd like to set up and solve for you a problem that uses ideas about forces and about Newton's second law and uniform circular motion to analyze how strong of a rope do you need in order to swing at the end of a rope swing. So here's how the setup goes. Imagine that you're attached to the end of a long rope and you're pretty high up, maybe on a tree branch or at a cliff, and you're going to swing into the water. And to have something to work with, let's just assume that you or whoever we're imagining swinging at the end of this rope has a mass equal to 70 kilograms. We'll figure that out later what that means in terms of the person's weight in both newtons and in pounds. And then let's say that the rope is about 5 meters long, so that would be 15 feet or so. And at the bottom of the rope, you're swinging at a speed equal to 10 meters per second. The goal is to swing back and forth, although maybe there's water down here in case you want to launch yourself into the water. So what we would like to do is try to figure out how strong does the rope need to be in order that you swing at the end of the rope without any problem. So let's first of all figure out how strong the rope would need to be if you were just hanging at the end of statically at the end of the rope. So you're hanging at the end of the rope. What would a diagram look like? Well, the weight vector would point down, the force on you by the earth, and you would calculate that by using mg, and then the rope would pull you up. So this force technically is the force on you by the rope, to use its full name. However, we often shorten those types of forces, the types of forces that are exerted by ropes and strings and cables and cords, to call them tension forces, because it's hard to say the force on you by the rope. We did the same thing with the weight. This is the force on you by earth because of gravity, and we shortened it to the weight. But let's not forget that this tension force is the force on you by the rope. And it's that thing that we need to figure out what it is, because if the rope can't support a tension more than the rope is rated for, then the rope will break. Well, if you're just hanging at the end of the rope and not yet moving, then your acceleration is 0. That would be true if you were moving up and down at constant speed too. But in this case, just hanging at the end of the rope, your acceleration is 0. So that means the net force has to be 0. And that would mean that the tension force, which points up, minus the weight force, minus because it points down, has to be equal to 0. So by looking at the acceleration, you figure out what the net force is. And by looking at the forces that are actually exerted, you figure out what forces make up the net force. So we learned that the tension force has to be equal to your weight, which would be equal to mg. Probably not a big surprise here. And if you evaluate that out to a number, if we use g as approximately 10 meters per second squared, and the mass is 70 kilograms, you get 700 newtons. On the other hand, if you want to know what that is in pounds, you can use the conversion between newtons and pounds. And if you look that up, I think you get somewhere around 150 pounds or so. So it's a pretty normally weighted person. So what sort of rope do you think you should buy if you wanted to do this experiment involving the swinging? Well, you could say, I'm going to buy a rope that can support 150 pounds and call it good. Or you might say, I want to have a little bit of extra margin of error in there. You might say, maybe if I double that, I would be safe. So maybe you get a rope that has a tensile strength of 300 pounds. Well, let's see what actually works. Let's make a free body diagram when you're swinging at the end of this. So swinging at the end of the rope. What's the diagram look like now? Well, you still have the weight force down, which doesn't change, and it's equal to mg. And you still have the tension force up, but I wonder how it has to compare to the weight force. I guess you have to ask yourself ahead of time, is there acceleration or not? And if there is, what's the direction of the acceleration vector? Well, I want to stress to you that behind all of this is the fact that you, or whoever's swinging at the end of this rope, is moving in a circular path. And anytime something moves in a circular path, then the centripetal acceleration needs to be taken into account. And the centripetal acceleration is v squared over r. So what does that turn out to be? Well, we said at the end of the rope that the speed was 10 meters per second and the rope was 5 meters long. So v squared over r, 10 squared is 100, divided by 5 gives you 20 meters per second squared. So that's the acceleration at the end of the rope. And by the way, it's directed upward, because the centripetal acceleration is always directed toward the center of the circular path that you're moving in. So now we know that the net force isn't zero. The net force has to be equal to ma. And a is this centripetal acceleration that we just figured out. Now what forces compose the net force? Well, still I have the tension force, which is up, minus the weight force, minus because it's down. This time they don't balance out to zero, they balance out to ma, where the acceleration is the centripetal acceleration. So if you want to find the tension force, you can just plug in numbers for things at this point and work it all out. I can do it maybe a little algebraically. I would say the tension force minus mg equals ma. And then I would solve that for the tension force, which is equal to mg, the person's weight, plus ma, which is mass times the acceleration. So mg was 700 newtons, and ma turns out to be twice that, or around 1400 newtons. The reason why I know it's twice that is because a is twice g. So ma is twice mg. So this is equal to 700 newtons, which was the tension force you needed if you were just hanging at the end of the string, plus an additional 1400 newtons to provide the upward acceleration to keep you moving on the circle. So the total tension force that you're going to need is 2100 newtons. By the way, that's 3 times your weight in this particular case. So if you lowballed the rope and picked one that only had a tensile strength equal to twice your weight, thinking you were building in a margin of safety, you would have made an error and the rope would have broken. Now it bears mentioning, which way would you move if the rope broke right here at the very bottom of the path? Well, I want you to realize that if the tension force is no longer present, the only force that would be present is your weight. And when things, the force of gravity, and when things move under the influence of the force of gravity alone, then they're in free fall. So what would have happened if the rope broke at the very bottom of the path? You would have had an initial horizontal velocity, but you would have been pulled down steadily by gravity, and you would have followed a projectile type path, which links up with ideas from the previous chapter.